All right, class. So we had completed the unit properties of matter, bulk properties of matter. So mechanical properties of solids was over and mechanical properties of fluids was also over. So now we'll start with a unit that is your thermal physics. So this unit comprises of 3 lessons. One is your thermal properties of matter. One is your thermodynamics, and last is your kinetic theory. Then we'll be left with just one more unit, that is SHM and waves and oscillations, which is. So I'll be starting today with thermal properties of matter. Thermal properties of matter. Now see, the thermal energy of a body is the total kinetic energy of all molecules of the body. Now, what is meant by this? I'll give you an example. What is meant by heat? Heat is the first concept that we are going to study. See here, let's say I have taken up a container here. And I have filled it with some molecules. Now, when these molecules are residing in this container, there will be certain motions exhibiting by these. So what will happen? Because of motion, there will be presence of kinetic energy. Now see, what will be the total energy of the system? Since these particles are moving, these particles are translating. So one will be translational kinetic energy. Translational kinetic energy. These particles will be rotating at their place. So they will be having rotational kinetic energies. And it can also happen that these particles are vibrating. Right? These particles can be vibrating at their place. So vibrational kinetic energy can also exist. Right. So these are the 3 types of kinetic energies that will exist. Now, other than this, what all types of energy can exist? This particle can be exhibiting force on this particle. These 2 particles can be executing force on each other. So due to force, due to interaction, we have one type of energy that is known as potential energy. Now, all these energies that are present within a system, we call all the sum of all the energies. If you add the translational kinetic energy with rotational kinetic energy, with vibrational kinetic energy, with potential energy, all the energies together, you get the internal energy of the system, which is the sum of all energies. Fine. Sum of all energies. Energies means kinetic energy and all the 3 types of kinetic energy and potential energy. See class, why do we have kinetic energy in the system? Wherever there is a function of motion, function of temperature, we get kinetic energy. You increase the temperature, kinetic energy will be more. This we'll see when we'll do the lesson of kinetic theory. That time I'll tell you the postulates. But for the time being, just remember, function of time is the kinetic energy, and function of force. Force, we say, how to identify force? By seeing the number of interaction. This is potential energy. Fine. Now see what will happen. So internal energy, I can write the total internal energy as kinetic energy plus potential energy. But see, one more thing that I'll tell you in detail when we'll be doing kinetic theory only, that time I'll tell you, you have the concept that if you have ideal molecule, if you're talking about ideal particles, that time, no, we do not consider potential. because we think that force will be zero for ideal molecules. We do not consider the forces that the ideal molecules exhibit. So for ideal molecules, potential energy becomes zero. So all the entire energy becomes equal to the kinetic energy. Now here this, listen to this. This is important. I have taken two containers. This is one container. This is another container. And I have filled both the containers with some amount of molecules. These are random, not water, any random molecules. This is A, this is B. Fine. Now see, the internal energy of this is the kinetic energy of this is UA, or let's say internal energy only, and this is UB. Initially, UA is greater than UB. UA is greater than UB. Means internal energy of A is very much greater than internal energy of B initially. Let's say internal energy of A is, take any number, let's say this is 5 joules. Fine. And let's say the total internal energy here is 3 joules. So obviously 5 joules is greater than 3 joules. It means internal energy of A is greater than internal energy of B. Now, what happens? Whatever is the extra amount of energy that will travel, let's say dq, that will travel from the one having higher temperature or higher energy to the one having lower energy. Till the time both have equal internal energies. This is finally they have same internal energy. So this amount of energy that traveled from the higher body to the lower body until both them had the same temperature difference, this is known as heat. This is what we call heat. Fine. This is what is meant by heat. I'm again repeating. Jania, you've joined quite late today. See, it's again I'm repeating in short. Listen to it carefully because heat is a very important concept in your thermal properties of matter. Internal energy is the sum of all the energies. How many types of energies can exist? Because the particles are moving ahead, they are translating, we'll have translational kinetic energy. The particles can be rotating at their position, we can have kinetic energy. Particles might be vibrating at their position, we'll be having vibrational kinetic energy. Also, they'll be exerting force on one another, so we'll have potential energy. Because kinetic energy is a function not of time, it's a function of temperature. Please make a correction here. This is a function of temperature. As you increase the temperature, kinetic energy increases. And potential energy is a function of force. So all the sum of all these entire energy, we call it as the internal energy of the system. So I had taken an example where two containers are there. One is having higher internal energy. Let's say A is having higher internal energy. So some amount of energy will flow. Let's say this was at 5 joules, this was at 3 joules. Now some amount of energy flowed from A to B. This became 4 joule, this decreased to 4 joule, and this increased to 4 joule. Now they are same. Now no more energy will flow from any of the direction. From either of the direction, no amount of energy flows. So that amount of energy, that had flown from A to B to make their temperatures equal, that we call as heat. So heat is the energy that is transferred from one body to another due to temperature difference between the two bodies. Heat is the energy that is transferred from one body to another due to temperature difference between the bodies. Am I clear? Tarif and Abdullah, I hope you must have understood. You were there earlier.
Misunderstood.
Okay. Note it down. Then we'll see the concept of thermal equilibrium and temperature. Yes, Tarif. See here. 2 containers I have taken. One is having extra energy. Let's say this is having this much of energy. And this is having a lesser energy. This is the energy. This is entire 5 joules. This is 3 joules. So to make them equal, how can you make them equal? You can only make them equal, no? Let's say, or don't look it like this. Take it in this way. You have 5 spheres here. I have 3 spheres. We want to make both of us having the equal number of spheres. So what you will do? It is only possible, no, if you lend me one of the spheres, if you give me one of the spheres, if this goes here, then with you also there will be 4, with me also there will be 4, right? This is equal now. Now, if you will give me more, then what will happen? I'll be having more, you will be having less. So that will disturb the equilibrium. Same thing is happening. You have 2 containers, you have filled it with molecules. Energy is existing, this is having more energy, this is having lesser energy. So some extra amount of energy, like this ball, this extra ball, the way it moved, same way this extra amount of energy will move to the one that is having lesser till both of them have equal. So the way this ball is like heat is basically this extra energy that is traveling to make both of them finally equal. Is it clear now?
Yes, clear.
Okay. So if you all have written, I think let's move forward. See, thermal equilibrium is the same thing. See, thermal equilibrium is not different thing. It is the same thing. See here, 2 containers you will take. That time I was just talking in terms of energy. Now I'll be talking in terms of temperature. This is having temperature A, this is having temperature B. So initially what will happen? Initially, let's say TA, temperature in A is greater than temperature in B. So that extra amount of heat will travel. This heat travels till when? Till the time both of them have the same temperature. TA is equal to TB. Now once TA is equal to TB, no flow of heat occurs. No flow of heat occurs. Fine. So this condition where temperatures are equal and no flow of heat can occur, this is known as thermal equilibrium. This is known as thermal equilibrium. Fine. Now there's a concept of temperature. Temperature is basically what? See here. The degree of hotness or coldness that decides the direction of flow of heat, that is known as temperature. How much cold a body is, how much hot a body is, that is decided by temperature. So that degree of hotness or coldness, and that always decides the direction of flow, because heat flows from higher temperature to lower temperature. So heat's direction is determined by this temperature only. And this entire branch of physics which deals with the calculations and the directions of heat and temperature, this is known as thermometry. And the device that measures temperature, this is known as thermometer. So thermometer working is based on just few types of physical quantities like volume, pressure. So when we use the thermometers, mercury thermometer, in mercury thermometer, we just see the volume of mercury. So that volume of mercury which is occupied in that narrow capillary tube gives us the reading of the temperature. Then you have resistance thermometer also, you have constant pressure thermometer, constant volume thermometer. But out of all these, this is just the first one is of use, volume of mercury, that is mercury thermometer. How is a mercury thermometer constructed? There's a bulb at the fine end of it. This bulb senses the heat. You have a very fixed lower fixed point. This is known as lower fixed point. Let's say it is 0 degrees Celsius. Then n number of divisions are made. And finally, at the end of thermometer, you will have the upper fixed point, which is the final most reading of it. So there are, depending on different types of scales, you have different types of temperatures, upper fixed point and lower fixed point. For Celsius, you have different. For Kelvin, you have different. For Reaumur, you have different. For Fahrenheit, you have different. So one by one, we'll see those. But do one thing, note down these 2 points first. Then I'll tell you the scales of temperature. Look here, for scales of temperature, you have 4 scales. So lower fixed point and upper fixed point I have written. For Celsius scale, you have the lower fixed point at 0 and upper as 100. So division will be 100 minus 0, means the lines that you see, the lines, number of lines which you see on the thermometer, that will be upper minus lower, that is 100 divisions. Then you have Fahrenheit scale. So lower fixed point will be 32°F and upper fixed point will be 212 Fahrenheit. So 212 minus 32, that will be 180 divisions. Then you have Reaumur scale. Lower fixed point, upper fixed point is 80 and lower is 0. So again, 80 minus 0 is 80 division. Lastly, you have one very important scale, Kelvin scale. Lower fixed point is 273.15 and upper fixed point is 373.15. Sometimes for the ease of calculation, this 0.15 is usually not written. This is written as 273 and 373. Out of this, Reaumur scale is not very important. Celsius, Fahrenheit, and Kelvin scale, these are important. Now, how do you write it? Any temperature is given, any temperature. Let's say this is some temperature X. Subtract it from the thermometer's upper fixed point, lower fixed point, thermometer's lower fixed point, then difference of upper fixed point minus lower fixed point. This will always remain constant. It means temperature in Celsius scale minus lower fixed point is 0 divided by upper minus lower, 100 minus 0 is 100, equal to, come to Fahrenheit. Let's say this is temperature of Fahrenheit minus lower fixed point. Lower fixed point is 32 divided by upper minus lower, that is 180. This is equal to, lower fixed point is 0. So for Reaumur scale, this will become minus 0 divided by 80 minus 0, that is 80. Lastly, you have Kelvin scale. Lower fixed point is 273.15 divided by 100. So this will be used whenever you will be solving any type of question. Let me show you one or two questions. Let's do. It says calculate the temperature at which Celsius and Fahrenheit have the same reading. So what is the formula for Celsius? Tc minus 0. This is Tc minus 0 by 100 equal to Tf minus 32 divided by 180. Right, from here if you look, this part and this part. Now it is saying they are having the same value, same reading. No, it means Tc is equal to Tf. Let's write this as T. So T by 100 is equal to T minus 32 by 180. Let's cross multiply. That becomes 180T is equal to 100T minus 32, 100. From here, we can write 80T equal to 3200. Temperature difference will be equal to, this will be minus, so minus 40 degrees Celsius. This is how you use the formula, same formula. Note down this part. See class, the next topic is thermal expansion of solids. So what is meant by thermal expansion of solids? Thermal means heat. Thermal means heat, and expansion means to increase. So the increment in the dimensions of solid because of heat, we call it as thermal expansion of solids. So increase in dimension of body due to increase in temperature. Suppose I have this body and I supply heat to it. I'll notice after certain time the length of the body will increase. Yes, that is how welding and rest of the iron works are done using fire and heat. So basically what happens if you talk about a very small portion from this, no, very small portion. Two molecules are like this. They are separated from each other by this distance. Once heat is supplied to them, these molecules expand, become far from each other. The separation between them increases. That's why the entire length increases like this. That is how the entire length increases. So you have three types of expansions of solid. First is linear, which is expansion in length, one dimension. Then you have superficial, which is two dimension. And then you have cubical or volumic, you can say. This is three dimension. So let me start with the first one, that is linear expansion. See, in linear expansion, what will happen? Suppose that I have taken a piece of rod. And this increases. This rod increases its length. Let's say original length was L naught at the time T naught. Now when the temperature is increased to T, length has become L. Clear till here? L naught original length, L is the final length. I'll write this. L naught is length. This is length at temperature T naught. Then you have L, which is the length at temperature. This is the length at temperature T. So obviously T is greater than T naught and L is greater than L naught. Final temperature, final lengths are greater. See, it was observed that whatever is the change in length, oh, can you see here a change in length? This was the final length, this was the original length, there's a change in length. This change in length is directly proportional to two things. Firstly, it is directly proportional to original length. Secondly, it is directly proportional to this temperature difference. What is temperature difference? Temperature difference is T minus T naught, final minus initial. Right, that is how we write it, final minus initial. So if you combine, delta L will be directly proportional to L naught delta T. You remove the proportionality sign, put an equal to with a constant. Constant here will be alpha, L naught delta T. This alpha is what? This is coefficient of linear expansion. See, if I want to write it, how will I write alpha? Alpha will be delta L by L naught delta T. From this formula, look here. Delta L by L naught. What is meant by this? Delta L by L naught. This is fractional change in length. This is fractional change in length. So the fractional alpha, how can you define alpha? Alpha is mainly fractional change in length per degree change in temperature. Fractional change in length per degree change in temperature. See, how can you write the change in length? Change in length can be written as L minus L naught. This is equal to alpha L naught delta T. Bring this L over here. L will be equal to L naught plus alpha L naught delta T. Take L naught common from here. What will you be left with? L naught 1 plus alpha delta T. Class, this is one of the very important formula which you have to remember from your linear expansion. Fine. This is one of the very, very important formulas which you have to remember. What is L? L is the final length. L is the final length. L naught is original length. L naught is original length. Delta T, this is the change in temperature. And what is alpha? Alpha is coefficient of linear expansion. How will you use this formula? See, I have one question. Using this, you can understand this. This question says that length of wire is 10 meters at temperature 10 degrees Celsius. It means original length is 10 meters. Original temperature is 10 degree. You have to find the length at temperature 20. So this length you do not know, but you have alpha as 2 into 10 to the power minus 4 per degree inverse. Yes, class, one more thing. The SI unit of this alpha, this is Kelvin inverse or per degree Celsius inverse. Because length here will get cancelled and only change in time temperature will be left. So see, L will be equal to L naught 1 plus alpha delta T. So delta T will be T minus T naught. Final is 20, initial is 10. So 20 minus 10. This will become 10. Change in temperature is 10. So L will be L naught is 10. From here, look, 10. 1 plus alpha. Alpha is 2 into 10 to the power minus 4. And delta T is 10. So once you will solve this, this will come out to be 10.02 meters. This should be your answer. Just check it once also. Any doubts you are having, let me know. Because this linear one is very important. If you will understand linear one, then understanding of rest of the others are very easy to remember. Fine. So first remember for the linear expansion. If you've understood linear expansion, then that becomes easy to understand the cubical expansion as well as the superficial expansion. So here we had seen a numerical as well. This numerical simply says you will use the formula L is equal to L naught 1 plus alpha delta T. Do one thing, note it from here, write down linear expansion, then we'll discuss cubical and superficial expansion. If you'll understand linear, no, understanding these are very easy. These are just based on linear. So that's why I'm saying wherever you are having any doubt, get it clarified. Note it. Any doubts you have, text me in between. Get it clarified. Ask me to repeat. I'll repeat it. C class. Similarly, you have superficial expansion. In superficial expansion, same things will be there, except for the fact that this is increase in the surface area. When the length increases, the increment is in one direction, that is in one dimension, the length, we say it is linear expansion. If area increases, that is two-dimensional increment is there, we call it as superficial expansion. So same thing, the change in the surface area, this will be directly proportional to original surface area multiplied by change in temperature. So here, when you will remove the proportionality sign, the constant that you get is beta. Fine. How will you write beta? Beta can be written as delta S by S naught delta T. Same thing, if you look over here, delta S by S naught, this is fractional change in area. This is fractional change in area. So this will be fractional change in area per degree change in temperature. Same thing, surface area minus surface area naught. This is change in surface area, right? Delta S can be written as S minus S naught. This is equal to beta S naught delta T. Shift this here, S will be equal to S naught plus beta S naught delta T. So S will be equal to S naught 1 plus beta delta T. This becomes the formula of it. This is the complete formula. S is the new surface area, S not original surface area, beta is coefficient of superficial expansion. This is not coefficient of linear expansion. Coefficient of linear expansion was alpha. This is coefficient of superficial expansion and change in temperature. I'll share a question also with you. See here, it says that area of a square is given. See, original area of the square is given as 20 meters square. At the initial temperature, 20 degrees Celsius. Then what happens? We have to find the temperature is 20 degrees Celsius. Okay, initial is 10 degree. Initial is 10 degree. This initial, this is given as 10 degree. Final is 20. So we have to find out the surface area, and beta is given as 5 into 10 to the power minus 5 Kelvin inverse. So surface area that we have to find, this will be original 1 plus beta delta T. Look here, delta T will be equal to 20 minus 10, that is 10. So surface area, this will be 20 into 1 plus 5 into 10 to the power minus 5 into 10. So your answer will come out to be approximately 20.01 meter square. This is how we use it, exactly based on that, right? Note it down. Then lastly, we'll deal with cubical expansion, then I'll stop. So superficial expansion is increase in surface area. Okay, lastly, we have cubical expansion or volumic expansion. You can say this is change. Cubical expansion is simply change in volume. So I've already written over here things simple. Here, what will happen? Initially, volume is, let's say, V naught at temperature T naught. Now the volume increases to V at temperature T. Increment in the volume, that is increase in 3 dimensions. This is also called volumic expansion. So volume expands. Like in the first one, linear expansion, length expanded. In superficial, the area expanded, and in cubical, the volume will expand. Now the constant that will come here is gamma, which is known as coefficient of cubical expansion. So this is fractional change in volume per degree change in temperature. Same way if you write delta V is V minus V naught. So V minus V naught will be gamma V naught delta T. Bring V naught this side, same formula you will get in terms of volume. V is equal to V naught 1 plus gamma delta T. Here, Kelvin inverse or degree Celsius inverse is again the SI unit. Question, let me tell you, one last question, then I'll stop over here. Volume of body at 10 degrees Celsius is 100 meter cube. So initial volume is 100 meter cube and the temperature, initial temperature is 10 degrees Celsius. You have to calculate its volume and density both. First volume we'll see and density also at a temperature 20 degrees Celsius. Mass is given as 20 kgs and gamma is given as 10 to the power minus 4. So let us find out volume first. V will be equal to V naught 1 plus gamma delta T. So V will be 100. 1 plus gamma is 10 to the power minus 4. Delta T again. See, delta T will be T minus T naught, which is 20 minus 10. That is 10 into 10. So this will be around 100.1 meter cube. Now density is simply mass by volume. Mass is given as 10. Right, mass is given as 10 by volume is 100.1. So this is equal to 0.099 kg per meter cube. First find out volume, using volume find out density. Note it down, class. Any queries, any doubts you have, I'm again asking from this entire lesson. Get it clear? All right, then we'll have, so this was a very important topic that we did today, heat and thermal expansion. Text me done class when you've completed.